So we're in the middle of covering the x86-64 assembly. So if you remember, the processor is nothing but big finite state machine, right? So we defined state. What is the state of the processor? And there are a set of registers. In x86-64, there were 16 general purpose registers. And also we have like program counter, which actually points to the next instruction to execute. And there are 4 flag registers or conditional code, right? So as a result of a computation, these 4 registers like carry, 0, sign, overflow, those 4 bits are set implicitly as a result, as a side effect of computation, right? So that's kind of state of the processor we have. And as we go on, like executing your program, instructions are executed one by one. And whenever you execute a new instruction, it actually moves to the different, like a new state, right? That's the idea. So I think I stopped here last time. So let's continue to cover how those like program constructs, such as loop, if then else, they are translated into assembly. So let's take a look. So in order to implement if then else or like a loop, we actually have to have like jump and branch instructions. Okay, so there are like different mixes, different like flavors of jump instruction. So if you actually have JMP, so generally this is called JX instruction because it's jump. Depending on the condition, you may jump or may not, right? Depending on the condition. So this one is called, the first version is just jump, JMP. So this one is unconditional. So whenever you hit upon this instruction, you actually have to jump to the address pointed to by this instruction. And the remaining instructions are conditional. So this one is unconditional. Sometimes this one is called jump. Unconditional jump. And those remaining instructions are called conditional branches. Conditional branch. Okay, so it's a branch because it diverges. Your program control may diverge depending on the condition. Whether for example, JE. This one is basically you jump to the target if 0 flag is set. Okay, so it's equivalent to jump equal. So if 0 flag is set, then you jump to the target. Otherwise, you simply go to the next instruction. That's the reason why it's called branch, because your program control may diverge depending on the condition. JNE is jump not equal. So in this case, if your condition is non-zero, like a 0 flag is like a not set, then you actually jump to the target address. Otherwise, you go to the next instruction, and so on, right? So we actually have all different variations: jump not equal, jump signed, jump not signed, jump greater than equal, less than equal, above and below. So above and below is kind of the greater and less, but in like unsigned version. Okay, so this one is kind of equivalent to greater and less, but it's applied to unsigned integer. Okay, so that's the difference. So that's all these conditions are shown in this like a second column of the table. So please take a look. So let's see how we can use those instructions to implement loops and if then else. So let's take a look. Here's a conditional branch example. Let's think about this simple function, appsdiff, which calculates the absolute difference between the 2 variables. Okay, this function takes 2 inputs, x and y, and it returns the absolute difference of the 2, like this. X minus y, absolute value of x minus y. Okay, so the way it's implemented is you first compare the value of x and y. If x is greater, then you take off y from x. Otherwise, you take off x from y. Okay, so that's how you calculate this value, and you compile it. You compile this code. You actually get something like this. So let's see what happens. So first, you compare the value of these two, input values, x and y. So we assume that those two value x and y are provided in these two registers, RDI and RSI. So if you remember, the CMP instruction does nothing but, do subtraction of the two. So in this case, we take off, it calculates RDI minus RSI, but we don't really, store the result back to the register. It just computes the difference, but it doesn't update the value of the register, right? So that's what CMP instruction does. So in this case, RDI minus RSI means like x minus y, right? So this instruction computes the value of x minus y, and in the next instruction, if this value is less than 0, JLE means that if x minus y is less than or equal to 0, then we actually jump to the point pointed to by label L4, right? If this condition is satisfied, then we jump to this point of the program. Otherwise, we simply go to the next instruction. Okay? So that's how we, implement this if then else clause. So if you see here, if this is kind of the opposite to this original program code, right? So in the original program code, you compare if your x is greater than y, then you do something. But in the assembly code, we do the inverse, right? If x minus y is less than or equal to 0, which means x is less than or equal to 0, y, right? If this condition is satisfied, then we go to else clause. This is the else, right? Otherwise, we just move on to the then clause, right? So that's how, this conditional, how we make this conditional branch, then else. So, you can actually implement, we can actually, illustrate the same code, C code, using like a go-to statement. So this one is our original C code, but we can transform this C code using go-to, which actually has the exactly same like format as the assembly language I showed you in the previous slide. So let's say, we first evaluate the condition and test. It basically computes, it generates a Boolean variable, whether x is less than or equal to y. And if this is satisfied, this condition is true, then we go to else clause, right, like this. Otherwise, we just simply go to the next instruction to calculate the then clause. And once you're done, you actually go to, both actually they go to the same, like, the exit, which is done clause in this case. So, they actually, in a sense, the program control actually diverges and converges again in this case, right? So if you have like if here, then you actually have then clause here, and also else clause here, right? And this part is else, and this part is then, right? So program control actually diverges depending on the condition, and they actually converges again. So here they actually, again, they actually come back to the same exit point, like done here, right? That's the program flow. So this one actually is kind of C version of the assembly code I showed you in the previous slide, okay, using the go-to. So let's think about more like general conditional expression translation. So think about this C code, value is assigned depending on the test. If that test is true, then the value will be assigned by like this expression. Otherwise, it'll be assigned to like this else expression. So in the previous example of calculating absolute difference, this can be simply written something like val equals x is greater than y, then x minus y colon y minus x. Then this one is kind of calculating absolute difference, right? So in the go-to version, we can do the same thing again. I mean, it's pretty similar to what we saw in the previous slide. So test is, in this case, n test is like a, not test. And if test is not, this, like n test is true, then we go to else. Otherwise, we simply assign the value with then expression. Okay, so this one can be rewritten using goto like this, right? In general. So in this case, we create separate code regions for then and else expression, and execute only one of them, right? Not both. So in any given at any given time, you execute either then or else, but not both, right? That's the idea of like executing like this conditional expression. But that's one way to implement this if then else. But there's another way, which is using like conditional move like last time, like weeks ago. So conditional move is another way to implement these conditional expressions other than using branches. So this one is we implement the same like a conditional expression without using branches. Okay, so that's way number 2, how we can implement it. So let's think about this C code again, this conditional assignment. Then the second way to implement this is using conditional move. Okay, so there's like a special instruction called conditional move, which does the following. So if this test is satisfied, then we execute the move instruction. Otherwise, we don't. Okay, so there's instruction called like move. You already know move instruction, right? There's another version called C move. So the difference between move and C move is C move is executed only if certain condition is satisfied. Then how you specify the specified condition? You actually put some suffix here, like LE, GE, or E. All these like a suffix you remember from the jump instruction. There are like different suffixes, like suffixes if you remember. Then you can actually put this like a suffix to execute this move instruction conditionally. So this one is introduced in like a 1995 x86 processor, and GCC tries to use them. So then why you use this conditional move? The reason is it will become evident during the second half of the class, second half of the course, because branches are it's not desirable for performance. If for example, your program actually has a lot of branches, then it's likely that your program actually doesn't perform very well. So we want to avoid using branches to maximize the performance of your program. Okay, so that's a reason. It'll become more evident for you during the second half of the course. So here is a version of the same code using conditional move. So let's take this like absolute difference example again. So we use the same code again. These two arguments x and y are passed through the two registers RDI and RSI, and RAX actually holds a return value. So here, let's see how it works. So if you see this code, actually there's no branch, no jump, right? No jump instruction in the code because we actually use conditional move instead. The idea is you execute both path, then path and like else path, but you effectively nullify one of the path. Okay, so let's see how it works. Here, you first copy of the value to the RAX register using move instruction, and you take off the value of RSI. So RSI actually holds the value of y. So this one actually calculates the value of x minus y, which is the return value from the then clause, right? And then what you do is you also calculate the value for the else clause. Okay, so you copy the value of RSI. So RSI actually holds the value of x to RDX, and then you subtract the value of RDI, which is this one actually holds the value of y, and you take off subtract the value of X from this register Y, then you actually compute the value of Y minus X. So you, regardless of the condition, you compute the value of the two return values, like X minus Y and Y minus X, right? And then here, this is the interesting part. So you compare the value of X minus Y. So in this case, again, this one effectively computes the value of X minus Y, right? So compare instruction, and this instruction is conditional move. So what this instruction do is if the condition less than or equal to is satisfied, that means X minus Y is less than or equal to 0, which implies X equals less than or equal to Y. If this condition is satisfied, then you execute the move. Otherwise, you simply ignore this instruction. That's what this conditional move does. So in this case, if this condition is satisfied, that means we actually have to execute this else clause, right? Because X minus X is less than or equal to Y, then this actually falls on this like a else clause. So in this case, before we return to the caller, we update the return value with this like a eval. What we calculated on this to the RDX register. Otherwise, we simply return the original value of then clause. Okay, so that's basically how we make use of the conditional move to implement this if then else. But there are some some caveats, there are some cautions you have to take before you use this conditional move. So when this conditional move can be effective and when it is not. So there are some bad cases for conditional move. The first case is when both expressions are very complex. Okay? Because in this previous example, so regardless of the condition, we actually compute the return value for both then and else, right? So that's kind of waste because we actually waste the computation because in the original version using branch, we have only executed one of the two paths, right? So in this case, this one actually have some waste because we actually have to compute the return value for the both case, and we selectively overwrite the value to the return register to return the correct value. So if both of these expression then and else are very complex, then there will be a lot of waste, computational waste, right? So so this using conditional move make sense only when these computations are very simple in both cases. And the second second bad case for conditional move is risky computation. So what will be the problem with this applying this conditional move for the second case? Like a val equals p. If p is true, then it's star p. Otherwise, it's 0. What's the problem applying the conditional move to this program statement? 왜 문제가 되죠? When the hint is, if you use conditional move, you actually have to compute the return value for the both, then and else, regardless of the condition. Okay, then what is the problem here? Is right. So that's the correct answer. Because if p equals 0, then actually you have to still dereference the pointer to access the memory location of 0. So which is which will actually for sure which will generate fault, right? So because you actually have to compute both values anyway, regardless of the condition, then this one have some this can put you in a dangerous situation because now you actually have to dereference a null pointer, right? And finally, the third, like a bad case, is computation with side effects. Okay? So in this case, let's think about it. So in original like a program statement, you only expect return value will be chosen from one of the two, right? But in this case, you actually have some side effect. So it's side effect meaning you actually have some, as a result of executing the statement, your state gets changed, right? Because in this case, this one updates value of the x with x times 7, right? This one will update the value of x with x plus 3, right? So in this case, you actually have some side effect. It not only returns the value, but also changes the value of x. But in the original program struct, you expect only one of these two will be executed. But if you use conditional move, that will be, both will be executed and change the value of x. So this one will be like, another like some bad case for conditional move. So compiler is actually smart enough to, it ever detects such a case, then it actually avoid using conditional moves. Risky computation은, let me explain in Korean. It's just a thing. 그러니까 P가 만약에 여기 이게 실행하는 게 어떻게 되는 거냐면 P가 포인터의 값인데 포인터가 만약에 0의 값이 아니면은 그러니까 밸리드한 포인터 값이면은 그 포인터에 있는 값을 읽어오고 아니면은 그냥 0으로 값을 어사인하는 이게 스테이트먼트잖아요. 근데 포인터가 만약에 널 포인터면은 만약에 널 P가 원래 0이면은 얘만 실행돼야 되잖아요. 그죠? 근데 그 컨디셔널 무브를 사용할 때는 항상 양쪽 다, 그러니까 den 쪽이랑 else 쪽을 다 실행을 해가지고 값을 계산해 놓은 다음에 그 중에 하나만 셀렉트하는 식으로 이거를 마지막에 컨디셔널 무브로 실행을 하기 때문에 어쨌거나 둘 다 값을 계산을 해야 돼요. 근데 0을 계산하는 건 그냥 뭐 컨스탄트니까 되게 쉽게 그냥 계산할 수 있는데 저거는 널 포인터일 때도 포인터를 그 0번지라는 주소가 가르치는 메모리 로케이션을 읽으려고 시도를 하겠죠. 저 경우에는. 그죠? 근데 그러면은 보통 0번지를 액세스하려고 그러면 세그 폴트가 발생하거든요. 그러니까 저걸 아마 실행하면은 만약에 포인터 어린 경우에는 100% 세그 폴트가 나겠죠. 세그멘테이션 폴트가 나겠죠. Any other questions? All right. So we're done with if then else, and let's move on to loop. By the way, this homework number 2, as I promised, homework number 2 will come out today, and it'll be a lot of fun. We're gonna reserve the last 15 minutes of the class for introducing the homework for you, and today's material and like a next lecture's material will be very helpful for doing homework. So please pay attention. All right. So let's move on to loop. So let's start with simple like a do while loop. Okay. Let's take a look your function on the left side. So there's C code called pop count. So pop count is let's say you have string of bits like a 32 bits. And pop count means, it counts how many ones are there in your like a bit stream. Okay, so let's say if you have like a 32-bit number, and it has a 1 0 0 0 0 0 like all zeros and 0 1 1. And what this function returns is how many ones are there in your value. So in this case, we have here, 1 here, 1 here, 1 here. So it will return 3 because we have 3 ones in your bit stream, right? So that's what this pop count does. This one is, it does very simple thing. It first initialize the result to 0. Initially we actually have 0 ones, and then we enter a loop. And what it does is it adds the value of x and constant 1. So let's think about this one first. So what does this expression do? So it and the value of x with constant 1, right? Then it only retains the value of LSB. But all the remaining bits will become 0 if you take end of the 2. only this bit will be filtered out, and the other one will be just set to 0. So if this value is 1, then you actually add 1 to it. If this value is 0, then you add 0 to it. So you update the result, and then you shift this original operand by 1 to the right. So we shift the entire bit stream to the right by 1 bit, and then we repeat this process until this value of x becomes 0. Okay, so that's a very simple function to calculate the number of ones in your value. So here is the goto version. So let's transform this C code using goto, which is more easily can be more easily translated into assembly. So here is like long. This part is the same. Result is initialized to be 0, and we actually have loop here. This is the label, and we do the same thing. Result is the same. Shift is the same, and this part is different. So we, instead of using like a while statement, we can unfold this while statement using this if. So if value of x is non-zero, then we actually go back to the loop. Otherwise, we simply fall through the next instruction, right? So this is the goto version. So let's take a look how this goto version of the code can be translated into x86-64 assembly. So here, we assume the RDI register holds the initial value of x, like this argument. X is held in RDI register, and RAX register will be the return value, so it will be held in RAX register. So here, we assume we initialize this, EAX or RAX register to 0. Actually, this line initialize the entire RAX register to 0 is the equivalent. And so it starts the body of the loop. We first, this one is kind of we compute the value of the result. I mean, we execute this part of the code using these 2 instructions, and actually these 3 instructions, because we first calculate this value, x and constant 1, and we add this value of t to the result value held in RAX, right? And we shift, this RDI register to the right by 1, and here we use JNE. So JNE is basically not equal. So if it's not equal to 0, then we go back to the head of the loop, L2. Otherwise, we simply go to the next instruction. Okay. So that's the almost like a direct translation of this like a goto version of the C code into assembly, right? It's the same pattern. So here is more like a general do-while transformation. Think about this do and loop body followed by while statement. Then if you actually translate it into goto version, then you actually have label loop here followed by the body, and there's like an if statement which actually tests the condition. So if this test is true, then we go back to the loop. Otherwise, simply go exit the loop, right? So this one is kind of converted version of do-while statement. And let's move on to how we can use like a while, how we can translate the while statement. So the previous one was do-while. So you first enter the loop, and at the end of the loop, you evaluate the condition, right? That's the do-while. But there's another version of the loop, which is while loop. So while actually does at the top of the loop. Looks like this. So if you use while statement, before we enter the loop, we first check the condition, whether it's true or not. And if it's true, then we enter the loop. Otherwise, we simply skip the loop. So that's the while loop. So here is a goto version of the while. So we first, go to the test. Because in the while statement, we have to first evaluate the test. And then if it's true, then we go to the loop body. Otherwise, we simply exit. So we first, at the beginning of the loop, we first go to the test. And then if the test is true, then we go back to the loop, like otherwise, loop body. Otherwise, we simply exit the loop like this. So that's how we implemented this while loop. And this is called like a jump to the middle version. Because in the beginning, we simply jump to the middle of the loop, the test part. And then we first execute the test. And if it's true, then go back to the loop header. Otherwise, simply exit the loop, right? So that's the kind of, that's the jump to the middle like version. So if you actually translate this C code, let's say you use while loop here. So this is the same like a pop count example, but using like while instead of like a do while. So let's say you have while statement, then you can translate to like a jump to middle version of the program like this. So you simply, we first, go to test, and then you execute this test part, and if it's true, then you actually go to the loop. Otherwise, you simply exit the loop, right? So this is kind of, translated to jump to the middle version, translated using like go to statement. And that's like a version number 1, jump to the middle. Whenever we start the loop, we first go to the test part and then, do the test first. That's version number 1. Here's version number 2 of the doing same thing. So here, we can convert this while loop into do while loop first, right? So in this case, we simply place like test code or preamble, maybe this is some people call it preamble. Before you enter the loop, you actually do some condition, execute some condition. So if this condition is not satisfied, then simply you skip the loop. You actually place a guard. You place a guard before the loop. And if this condition is not satisfied, you simply skip the loop. Otherwise, you enter the do while loop. It actually does the same thing, right? So you already know, how we translate this part because, a few slides ago, if you remember, do while translation. So this one, right? So if we apply the same like transformation to like this case, this part, then this part will be translated into like this, and this part is the same. Okay. So this is called like a do-while conversion. So your while loop is first converted into do-while loop, and then the compiler actually generates code for the do-while loop. Okay. So if you actually take this this version, so here is a C code, original C code, which is translated into do-while version using like a do-while conversion. So here, if this condition is not satisfied, then we actually skip the loop. Otherwise, we enter the loop. This is do while, right? This is a do while loop, right? So that's basically how we convert this C code into a do while loop. And you can actually use the same basically translated assembly code as do while in this case, right? It's the same code can be reused here. Finally, maybe the most general form is like a for loop, right? The for loop actually has three things: initial value, and test and update, followed by the body of the loop, right? So we can rewrite the this pop count function using like a for loop, like a for 0 through with word size, and you basically you take a look at every single word, and if it's 0, then you add. If it's 1, you add 1 to it, 1 to the result. Otherwise, you simply drop it. So this is a for loop version of the pop count. So here is the initialization part, like init, I equals 0. Here's the test part. So test part is I equals less than word size. You still continue the loop. And update is you update the value at the end of the loop, right? And this is the body. So this one is like decompose your for loop into like 4 components: init, test, update, and body. Right? So you have 4 components here. Then you can actually convert this for loop using while. So if you see here, there are 4 components: init, test, update, and body. And you execute init outside the while loop, right? And you test the condition like at the beginning of the while, and it's followed by the body, and at the end of the loop, you execute this update part, right? So they are equivalent, right? They are equivalent. So you can simply rewrite this for loop using while. And if you actually apply this transformation to the existing like this pop count function, then it'll look like this. Init, test, update, and body. So init goes here because we have to execute this init before we enter the while loop. And this test is the same here. And update is placed at the end of the loop because we have to execute it before we finish the iteration of the loop, right? So update goes here, and the body stays here. So that's the kind of transformed version of this original for loop. And so if you actually apply this convert this this while loop using like a go-to statement, then it'll look like this. So now we should do like a further transformation from like a while version of the loop to the go-to version. Then this one will look like this. And so initialization is here, not test is here, body, update, and test are placed here. Okay? So this basically how we convert this while loop to do while, and do while to go to, right? So we went through the several steps of conversion to get like this version of the code. And one interesting thing is this like init test version can be just optimized away, right? Because this is always true. Think about it. So here, value of I is initialized to be 0. This one is like constant, right? And W size is basically how many bits are there in your like input, right? So this is constant. So this value will be like a constant. If you have like 8-byte value, like quad word value, this one will be 64. So this comparison will be returns always true. Actually, always false. Actually, this is always true. So if you take not of it, this one will be always false. So you never skip this like initial. You never skip this loop. So in this case, this one can go away. Again, this compiler is smart enough to optimize this like unnecessary check away. Okay. All right. Any questions? I did a bunch of like transformation from like do while, actually for to while to do while to go to. We actually went through like multiple steps of transformation, and then eventually we translate this like a go-to version of the code into assembly to get the final version. Okay, so no questions. So we move on to the switch statement. So how we can translate this like a switch statement into assembly? So let's think about this example. Very long switch statement. What you know switch case statement, right? If you have like a switch, then depending on the value of x, you go to a different like case, right? So in this case, you actually take the value of x as input. If x equals 1, you go to the case 1. If x is 2, then go to case 2. X is 3, then go to case 3, and so on, right? You just simply go to the right place. There are some interesting cases. So here are like multiple case labels. In this case, you actually share these two cases share the same body of the code. So if the value is either 5 or 6, and they execute the same code like this. Right? This is kind of sharing case. And the second interesting case is like a fall through. One of the kind of very common bug you guys when you write the code is you miss break statement, right? So whenever you're done with your case, you actually have to place a break, right? Then you actually skip the rest of the body, and then you go to the next, line, right? But sometimes you guys make a mistake. to not place this break, and then you keep executing the remaining body of the loop, the remaining body of the case statement, right? So this one is kind of interesting case. There's no break here. So if there's no break, you are supposed to fall through. Fall through means just move on to the next statement, right? So this is a fall through case here, like case 2. And also there are like missing cases here, like a 4, or 0. Also like a 0 is also missing. Case 0 is also missing here. So case 4, case 0 are missing. So whenever there's a missing case, you actually have to go to default case, right? So if there's any match, like from like with this x and one of these like expression, then you simply go to the case. Otherwise, if there's no match, you go to the default, right? This default value, like this. So your switch statement must handle all of these cases correctly. So to use like a switch statement, to implement switch statement, compilers generally employ what is called jump table. Okay, so jump table is basically nothing but a big like table which takes the variable x as input and returns the target address for that like value as output. Okay, that's jump table. Value of x is in, and the target address for the x, that x is out. Right? That's the jump table. So here's jump table. What the jump table looks like. Let's say this block 0 starts at target 0, and block 1 starts at targ 1, and block n-1 starts at targ n-1, and so on. Right? Then this jump table actually holds all the addresses of this like a starting position of each code block. Okay. And once you actually have jump table, your switch statement become very easy to implement because now you can simply jump to the jump table x. So basically go to the address which is pointed to by the entry in the jump table, right? So that's basically how you implement this jump table, like jump instruction, like a switch statement. So here is the typical like implementation of a switch statement here. This switch statement. So let's assume the arguments like x, y, and z are stored in RDI, RSI, and RDX registers. And then RAX actually holds a return value because in this case, return value is W. That's the assumption. So here, if you see the switch statement, you first copy the value of RDX, like argument of Z to RCX, which is, you simply just copy it. For some reason, maybe it's updated in the later statement. So simply you copy the value of Z in the first move instruction. And then secondly, what you do is you compare the value of RDI over constant 6. So what this compute is, it computes RDI. The value of RDI is basically value of x, right? So this one computes the value of x minus 6 without updating the register. So this is compare instruction. And then in the next instruction, you compare the value. If it's jump above, right? Above is like a greater than. So if x minus 6 is greater than 0, then you actually go to the place of label number 8, L8. Okay? Basically, this L8 what this L8 will point to? What is this code block labeled L8? Where should this one go? If x is greater than 6, what code should be executed? The previous here. If x is greater than 6, default, right? So L8 will be the starting address of the default. So here, if you come back, so we first compare the value of x over 6 against 6. And if x minus 6 is above is basically greater than, but applied to the unsigned integer, right? So if it's greater than x minus 6 is greater than 0, we go to label L8, which is a starting address for the default. Okay, refers to the range checking. Refers to the range checking for the value of x. Otherwise, if the value will be somewhere between 0 and 6, right? Otherwise, we go to the address pointed to by the jump target address, jump table. Okay, so I'm going to explain this part in more detail in a few slides. So don't worry too much about it. But the flow is basically you first check the bound of the value of x. If it's out of a bound, then you go to default. But if it's inbound, then actually you refer to the jump table and jump to the address pointed to by the entry in the jump table. So here is the what this jump table looks like. So jump table looks like this. Jump table actually starts at the location L4. So this is kind of the initial, like a starting address of this jump table. And there are like 7 entries. 1, 2, 3, 4, 5, 6, 7. 7 entries, right? Because this jump table is supposed to hold like target address for 7 entries, 0 through 6. This one is for like x equals 0. This one is x equals 1. This one is x equals 2, x equals 3, x equals 4, x equals 6. So there will be like 7 entries for the value 0 through 6, inclusive in both sides. 0, 1, 2, 3, 4, 5, 6, 7, 5, 6. So these are basically target address for each case. So let's think about this case one by one. So here, this one is by the way, this is called indirect jump. So this one is you know how to calculate this part already, right? So this part is kind of you calculate the address. So this is a displacement with scaling, right? So this one will be calculated as that L4. So that L4 will be the starting address of the jump table, like the base address, jump table, plus percent RDI times 8, right? So that's what the address. If you calculate this part, and star means instead of like directly jumping to this address, you jump to the value at that like position in memory. Okay, so it's like indirect jump. So here, here's more details. So here's a table structure. Each target requires 8 bytes. Each target, here, we have 7 targets, 0 through 6, and each target requires 8 bytes because we are assuming like a 64-bit architecture. So address is like 8 bytes. And jumping. So if you remember, this is a direct jump. So direct jump means you jump to the location, labeled .L8. So, jump target is denoted by label L8 in this case. This is called direct jump because we directly jump to this address. But, if you actually have a star here, this is called indirect jump. So indirect jump is, you calculate the value of this part. As I said before, this part will be return effective address of L4 plus x times 8. So this one will be the effective address. So once you calculate the address, so let's say x was like 3. So if x was 3, then this expression will return the address for this entry, right? Because this is like a 0, 1, this is the entry you're looking at. So if you actually have a star, instead of jumping to the location of L, like a jump to here into the jump table, you actually read the value from like this jump table, and you actually jump to L9. That's what this indirect jump does. Okay? 그러니까 다이렉트 점프는 그 여기에 있는 오퍼랜드를 그냥 그대로 읽어서 그 주소로 그냥 바로 뛰는 거고, 그죠? 인다이렉트 점프는 요 주소를 계산한 다음에 그 주소에 있는 메모리의 값을 읽어와서 그 값으로 뛰는 거죠. 그게 다이렉트 점프와 인다이렉트 점프 차이죠. 스타가 있냐 없냐에 따라서, 그죠? So that's the difference the difference between direct and indirect jump. So here is the jump table. So here, we actually have like 7 entries. It'll be mapped to like this. So case number 0, because we don't actually have case 0 here. So because we don't have case 0, this one simply go to default, right? In case of case 1, so case 1 actually points to the code block L3. So L3 actually starts here, like code, this x equals y times z. So this one actually is, the code block at L3. Case 2 is here, so it's pointed to by L5. And this one is pointed to by, the third one is pointed to by L9. And like X4, again, there's no entry for case 4. So in this case, this one actually points to the default, which is L8. And the remaining two, like 5 and 6, they actually points to the same target, like L7. Okay? So in that way, you can implement some arbitrary, table like this, like a switch statement using jump table. And all of this, like jump table creation and labeling, all this thing is done by the compiler. Compiler takes care of, creating this jump table and then label all of these code blocks and then create the right mapping between the code block and this jump table. It's all handled by this the compiler. So let's take a look at the code blocks. So in case of in case number 1, case 1, so this one actually starts at the label L3. So if you take a look at the L3, so it actually computes the value of RSI to Y, because RSI actually holds the value of Y here. So we simply copy the value to RAX register, and then we multiply the value against RDX. So RDX actually holds this value of Z. So it computes the value of Y and Z and store the value into the RAX register and then return. This is like case 1. Let's think about this fall through case. So fall through is, in this case, there's no break, right? Because there's no break. If you start executing like case number 2, then you actually have to finish case number 2 first and move on to case 3, right? Because you're supposed to fall through to the next case, right? So in this case, it looks like this. You first execute Y, this W statement, like this value of W, and you go to merge. So in the merge, you actually calculate this W equals W plus Z. Okay? What happens if you go to case number 3? So if you go to case number 3, you actually have different value of W, right? So in this case, this initial value of W is supposed to be 1 because we actually initialize the value of W here. So if you go to case 3, in this case, the initial value of W will be 1. So it will be equivalent to W equals Z plus 1, right? Because W is initialized to be 1. Therefore, if you go to case 3, you first initialize the value of W to 1, and then you execute the same like a statement like this. So in case 2, you go to here and go here like this. In case 3, you go to here and go here like this. So here's the code block which actually implements exactly what I told you in the previous slide. So here, in case 2, you first calculate the value of division. You divide the value of Y by Z, and then you go to this the code block labeled L6, and L6 is like a merge code. So you add the value of Z to it. So that's what's done. And the case 3 actually starts from L9, from here. So in this case, you first initialize the value of RAX or EAX to 1 first, and then you add this value of Z to this RAX value and return. Okay? By the way, this CQTO, like convert to octword, this one is kind of the necessary instruction for using like a division, because in Intel x86 architecture, when you divide, your dividend is actually 128 bits, and divider is 64 bits. So let's say you divide A by B. This is dividend. this is divider, right? And Intel x86, if you use the IDIV instruction, this one must be 128 bits. And this one is like 64 bits. So, you know, this CQT, what this CQTO instruction does is it extend the initial, this operand, one of the divider operand to like 128 bits. That's what it do. So how you can extend it to 128? By using 2 registers instead of just 1. So in this case, if you execute like this instruction, you always place your dividend in RAX, and RAX hold like a low 64 bits. Low 64 bits of, you know, dividend, this one. And if you execute a CQTO, then upper 64 bit will be sign extended from this like RAX to RDX register. This is kind of detailed. Don't worry too much about it, but it's just in case some of you may be curious. So in this case, you know, this like a dividend will be held in RDX register and RAX register together, because you're using 2 registers. We actually hold like one operand of 128 bits. And you know, this like a divider is actually stored in RCX register, so it's like 64 bits. So you know, it does the division. Code block like 5 and 6, you know, the default, then it looks like this, because they jump to the same like label, L7. If the X is either like a 5 or 6, then you know, you actually go to the same code block, and L8 is the default, right? The default value. All right, so I think this concludes this like lecture of this control part of this assembly language. You know, we covered if then else, do while, and switch statement. And you know, this one actually basically, they are all like control instruction. They change the flow of your program, right? It goes to somewhere, go to one place or the other. You know, this is kind of control, changing control of your program. And you know, so next time you're gonna cover this stack and call and return and all this like function calls on Thursday. Before we finish, any questions? Feel free to ask me. Otherwise, 예를 들어서 어떤 거예요? 일보다 작은 거. 근데 그거 스위치 스테이트먼트의 그거는 항상 그 언사인드 인터벌하고 가능하기 때문에 내가 체크하지 않아요. 0은 체크해야 되겠죠.
Yeah. Hello, everyone. I'm Daeun Kim. Before we start, did you check your Lab 1 score on ETL? I've uploaded your score, so please check your Lab 1 score. If you have any problem about your score, please come to me. So now I talk about the second lab called bomb lab. Maybe it's very funny and exciting homework you may expect it. So the mission is defusing a binary bomb is to enter the correct strings. To solve this lab, you learn about x86 assembly language, which is learned from the lectures. Based on the languages, you understand how to make array, switch, or loop with assembly code. Also, you learn how to use the powerful tools to debug your executable files, such as object dump or GDB. There are important things. You must use Martini server to execute and test your bomb. You cannot run your programs on your local machine or other Linux environment. If you lost or did not know your Martini account, please come to us and receive your ID and password. So first thing is, you access the address on the internet browser, martini.snucsd.org. The port number is 15213, and fill in the form and click the submit button. Then you can get bomb file. And in that file, you README and binary file and source file bombc are compressed. Also, we do not warranty your score if you enter your wrong student ID. The next is defuse your bomb. You can execute your bomb as above figure. If you execute your bomb, you can see this message. However, since you need to find correct strings for defusing your bomb, you should execute your file with a debugger or other tools. Also, this ref has 6 phases and 1 secret phase. Secret phase does not affect your whole score, so you don't care of it. Each phase has its own correct key. If you enter the correct key, then your bomb is defused and goes to the next phase. If not, then your bomb is exploded and you lost your life as a score. So I recommend you run your programs with other debugging tools. Now I explain about how to see and find the correct key. You can see only main routine file, bombc, to help you understand about whole pictures. To defuse your bomb, you need to look inside the bomb by this assembling, which translates executable binary to assembly code. You can track this assembled code using debugger or object dump tool. So I talk about a disassembly tool called object dump. Command object dump -t bomb gives you information such as functions, global variables, the functions bomb calling, and their addresses. Command object dump -d bomb gives you a disassembled code in the bomb. You can see every assembly function code and .text and .data parts. Also, you enter the man object dump command for more information about object dump. However, object dump shows a static version of program. It is impossible to see the variable's value and function call on runtime. That's why I tell you a GDB. While object dump is a powerful tool, GDB is a very, very powerful tool to debug your program. It allows you to see what is going on inside another program while it executes. It can also start your program specifying anything that might affect its behavior and make your program stop unspecified conditions using commands. What is better, you can see what happened in your program when your program has stopped and change the values in your program. Basically, Martini server supports the GDB program, but if it is not installed, use this command above, sudo apt-get install GDB. You execute your program as GDB program name. In this homework, you enter the command GDB bomb. Now, I let you know the basic instructions for your lab. You usually use this command. The first is run. Run is start your program until meeting a breakpoint. Continue is continue your program from breakpoint until meeting another breakpoint. Breakpoint makes a breakpoint. breakpoint command makes a breakpoint, you should enter additional arguments such as specific address or function name. For example, if you enter breakpoint and phase 1, then your program pauses before you enter the function phase 1. Delete means delete a breakpoint. It also requires additional argument such as function name or address. Step executes next line of code. If next line is a function, then it goes into the function. And next is the same as step, but it goes not into the function. If you want to quit GDB, then press Q, then the GDB is exit. And disassemble function name, disassemble the functions or lines of code. You use this command to see your BOM phases or main function. Here are print instructions to see variable. P function name gives you a function address, and print variable gives you a value of a variable var. If you change the variable format, you enter with the format such as T, O, D, and so on. Since P variable shows pure binary values. If you see memory values, you enter X address with range and format. If you want to know all register values or locations or breakpoint, enter the info register or info breakpoint. If you need more instruction details, enter help in GDB or man GDB or Linux terminal. And this is the important part, grading guideline. When your BOM explodes or diffuses, it notifies our server automatically. You can get points when diffusing each phases. Since 5 and 6 phases are hard to solve, they give you 20 points. Other stages give you 15 points. Also, you will lose your points when your BOM explodes. If you explode your BOM twice, then you get -1 point. Some guys think, if I mistake about 200, then should I get 0 scores? But don't worry. The maximum point you lose is 20 points. Also, due date is October 24th at midnight. And we will shut down the grading server after 3 days because of general grading. Also, you can check your points on this address, and it is updated every 30 seconds. You can download new BOM repeatedly using same ID, but though you diffuse many BOMs, your maximum points will be 100. This is the end of the BOM lab guideline, and if you have any questions, please ask me.